Good morning, students. Today, as we have already planned, we will start with our syllabus topics. Fine. The first very theorem we are going to prove here is Rolle's theorem. After that, mean value theorem. But prior to Rolle's theorem, you should be knowing the critical point of a function. What is the critical point of a function? Right? And also extreme value theorem. There is one theorem known as extreme value theorem, and another result is also there. Okay. So this finding critical points you have done it in PUC, but here it is going to be again a bridge course for you. I told you in every class you will have a bridge course. Okay. So finding critical points, that job you have taken up, but in order. Before visiting these things, please have a look at critical point definition. Okay, I just give you critical point definition here. Okay, when you call x equals c is a critical point, for the function y is equal to f of x. Yeah, a number x equals c is called a critical point for the function y is equal to f of x. When? If either f dash c is 0, the value of the derivative at c is 0, right? Or value of the derivative at c does not exist. Value of the derivative at c does not exist. And in addition to this, we have one more condition, that c should be the value c. Value c is the number which you claim as critical number. The number which you claim as a critical number is c here. C must be in the domain of the function. Okay. So let me repeat the definition of critical point. A critical number for a function f. A number x equal to c is called a critical point for a function y equal to f of x. If either f dash c is 0, value of the derivative of the function at x equal to c is 0, or derivative value does not exist, right? And plus the value c should be in the domain of the function, right? Either f dash c is 0 or f dash c does not exist, and in addition the number c must be in the domain of this given function. Then only we can call x equal to c as a critical point of y is equal to f of x. It's clear, right? Either f dash c is 0 or f dash c does not exist, and c should be in the domain of the function. This much should be guaranteed. Critical point. I'll give an example of critical point here. You don't look at the Rolle's theorem and other theorem right now. Just I have made it ready for the next use. Okay. You can critical points matter. The critical points. Fine. You look at an example. You take very simple example. You take f of x equal to x square. You know that it's a parabola. Parabola y is equal to x square is a parabola. It is symmetric with respect to y-axis. It's a parabola. Fine. Differentiate model. What is the domain of the function? Domain. What is domain of f? X square, that is a polynomial term. It is defined everywhere. At each point x, real x. At each real x, x square is a real number. It is defined everywhere. So domain of this function is set of reals. Set of all reals. You need not restrict the values. Any real number is okay. Square of a real number is always a real number. There is no problem here. It is domain. You want to know what is the critical points. Find f dash x. F dash x is equal to 2x. Derivative of x square 2x. Ask a question. F dash x is 0 value. This is f dash x is 0 ಅದರ value 2x. 2x is 0. 2x 0 because x equal to 0. So So when x equals 0, derivative is 0. Right? When x equals 0, derivative is 0. Derivative value is 2x. 2x is a polynomial term. It is always a real number. Derivative is always a real number. Always for each value of x, for each real value of x, 2x is always a real number. 2x is always a real number. Therefore, 2x equals 0 implies x equals 0. So, derivative exists. Hagaದ್ರೆ critical point ಯಾವುದು? Derivative exists ಇರುವಾಗ critical point ಗೆ other channel ಯಾವುದು? It is a point at which derivative is 0. Derivative is 0 at x equals 0. So, 0 is a critical point. X equals 0 is a critical point. Critical point ಅಲ್ಲಿ ನಿಮಗೆ local maxima or local minima you can find. Local maxima or local minimum. ಇಲ್ಲಿ local minimum value. Local minimum value. At the critical point, you have local minimum value. Critical point, right? Critical point is a point at which local extrema may occur. ಇಲ್ಲಿ local minimum value to 0 is a critical point. It is a point at which derivative is 0. It is C value. Critical point is C and there C. Whether 0 is in the domain? Yes, it is in the domain because domain is set of reals. 0 belongs to the domain. It belongs to domain. Right? So 0 is a critical point. You ask the second question. Okay, what is the critical point of the function? F of x equal to 1 by x. F of x equal to 1 by x is y is equal to 1 by x. Y equal to 1 by x is x into y is equal to 1. X into y is equal to 1. Or it is on the form x into y is equal to c square form. Can any one of you can identify the curve? Are you able to identify the curve? X into y equal to c square. X into y equal to c square. See, we will study geometrically first, mathematically next. Critical point geometrically first. Geometrically means by drawing the graph of the function and watching the graph and deciding. If y equal to 1 by x, x into y equal to 1. Those who have studied your second PU topics, first PU topic, conic section thoroughly may be in a position to identify this curve. X into y equals c square is a rectangular hyperbola. It's a rectangular hyperbola. Hyperbola has got two parts, the right branch, left branch. Right branch, left branch. For a rectangular hyperbola, you are having the asymptotes. X-axis and y-axis are called asymptotes. X-axis and y-axis, these are asymptotes. Asymptote is a tangent to the curve at infinity. So x-axis is the asymptote, y-axis is also the asymptote. X and y axis are asymptotes. Now you look at the curve. Parabola has got two parts here and here. It never meets the x-axis nor meets the y-axis. The part of the curve, the two parts of the curve, they neither intersect x-axis nor intersect y-axis. Fine. So since they does not intersect x and y-axis, no part of the curve is there at x equal to 0. At x equal to 0, there is no part of the curve. So 0 cannot be critical point here. 0 cannot be a critical point, right? And since there is no part of the curve at x equal to 0, neither local maximum nor local minimum exists. Local maximum this can be extended. This can be extended on either way. This can be drawn down here. This line you can extend towards minus infinity. Therefore, neither local maximum nor local minimum. There cannot be a critical point at x equal to 0. Now we study this mathematically. For this function y equal to 1 by x, what is f dash domain? Domain is set of all real numbers. Which value you want to exclude? 0. X equal to except x equal to 0. 0 cannot be a member of the domain because 1 by 0 is undefined. Fine? Okay. What is derivative f dash is? It is 1 by x derivative ಅಂದರೆ minus 1 by x square. Right? Ask the question. Can derivative be 0? Can derivative be 0? You ask the question. No, it can never be 0 because numerator is constant. Numerator is fixed. Numerator is fixed, it is equal to 1. Since numerator is 1, 1 cannot be equal to 0. Derivative is never 0. Now, critical points can be found in two channels. One is points at which derivative is 0. Please don't look at this one. Point at which derivative is 0 or point at which derivative does not exist. These are the two channels where you can search for critical numbers. But derivative can never be 0. So searching of critical numbers in this channel is not possible. Remove that. The only channel left out is this. To find numbers at which derivative does not exist. Derivative value is here. Clearly at x equal to 0. At x equal to 0 derivative does not exist. At x equal to 0 derivative does not exist. So f dash 0 does not exist. F dash 0 does not exist. Let me repeat the definition of critical point. Critical point is a point at which either derivative is 0 or derivative does not exist. Derivative is not 0 here, so searching here is not possible. Derivative does not exist. The case occurs at c equal to 0. Now you have to come to the last part of the definition of critical number. Derivative at 0 does not exist is a fact. 1 by 0 is not a real number. Now ask a last question. Whether this 0 is in the domain of the function. Right? In order that x equal to 0 qualifies to be the critical point, it should be in the domain of the function. Whether 0 is in the domain of the function. 0 is it in the domain of the function? No. Domain consists of all real numbers except 0. It is not in the domain. Since 0 is not in the domain, right, we don't have a critical point at all. Neither through f dash c 0 or not through f dash c does not exist. Critical point yava channel alli sigta illa. There is no critical point for the function here. That we have watched. That we have observed through the graph. Graph alli nodiddeve ನಾವು. There is no critical point for this function. Right? At 0 derivative does not exist. But here ನೋಡಿ derivative at 0 there is no part of the graph. Graph is part illa 0 dalli. Since there is no part of the graph exists there, then where is the question of local maximum, local minimum, etc. So this function 1 by x, it has no critical points. So for a given function, there may exist a critical point or may not exist. Fine? Okay. So let's say about critical points very briefly, since we are going to discuss these critical points later on. I leave it at this stage. Please look at these two theorems here. The first one is called extreme value theorem, Theorem 1. Extreme value theorem. Read that. If a function y is equal to f of x, y equal to f of x is continuous on the closed interval ab, right? Then f has an absolute maximum and absolute minimum on the interval ab. Continuity implies the possibility of absolute extrema. The theorem 1. I repeat, I am going to rub this because I need some more space in the board to write. Okay. Please listen, understand, store in the memory what is extreme value theorem, that is theorem 1. Extreme value theorem we are going to use in the proof of Rolle's theorem. Rolle's theorem proof alli ನಾವು extreme value theorem ಯೂಸ್ ಮಾಡ್ತೇವೆ. So ನೀವು ಈಗ ಇಮಿಡಿಯೇಟ್ ಆಗಿ ಅದನ್ನು ಮೈಂಡ್ಗೆ ತಗೊಂಡ್ರೆ what is extreme value theorem? If a function is continuous in a closed interval ab, closed interval ab ಅಲ್ಲಿ continuity ಇದ್ರೆ, you know what is closed interval and open interval? Closed interval ಅಂದ್ರೆ end points are included. If you take an x belongs to this, your a is less than or equal to x less than or equal to b. Closed interval andre any number you take here x can be the left end point or right end point or any value between that. X may be either left hand point, either A or B or any value between that. What do you mean by open interval? This is the bracket you are using for open interval. Please understand this very carefully. The notation is closed interval, the other one is open interval. What is open interval AB? Open interval AB means if you take an x here, then that x is strictly greater than greater than A and less than B. X lies between A and B. It is neither equal to A nor equal to B. Closed intervally end points are included in the set. Open intervally end points are not included, but any value between A and B are included. Solve it? Okay. So having noted open and closed, what is extreme value theorem says? If a function is continuous in a closed interval, then it is likely to have an absolute maximum and absolute minimum in the closed interval AB. The first theorem. Please store it in the memory. I remove this. Okay, theorem 2 learning. Statement of theorem 2 also you have to remember, because we are going to make use of both the theorems in the proof of Rolle's theorem. Right? This is actually prerequisite. Did you study this earlier? No. If you have not studied this earlier, we will discuss it whenever we get some time. Right now, you can assume this theorem. Assume what? If a function f has a local extremum is either local maximum or local minimum. Local extremum at an interior point C, interior point or interval in an interval AB. What do you mean by interior point? Interior point means any point C which is in between A and B. Between A and B, A and B is an interior point. Interior point, exterior point, you understand? Interval is the interior point. Interior point C and the interior point C means your C belongs to the open interval AB. Open interval AB is there. It is neither equal to A nor equal to B, but it is between A and B. It is open interval AB. It is open interval. Right? Okay. If f has a local extremum, right, local maximum or local minimum, at an interior point C of the domain, and if f dash C exists, if the derivative exists, then derivative value should be 0. Derivative value should be 0. The conclusion is this: derivative value is 0. This is theorem number 2. Theorem 2, if f has a local extremum value at an interior point C of the domain, then if f dash C exists, if the derivative exists, its value will be 0. Its value will be 0. This is the second theorem. Theorem 1 is extreme value theorem. Theorem 2 is a theorem where you have the conclusion f dash is 0. You have the conclusion f dash is 0. So, this is theorem and Rolle's theorem use one. Okay. So, remember both the theorems. Fine. Okay. Now we come to the first main theorem of your first SEM BSc syllabus. First SEM BSc, right? Syllabus only. I think you are in which unit? First SEM BSc. You are having 4 units. This is the syllabus. It is unit number 1. Unit 1. So what we are going to begin here is unit 1. Unit 1. Unit 1 only, right? You are having increasing functions, critical points, then the recapitulation, no? And Rolle's theorem. Rolle's theorem is the first theorem. Prior to this, I have just mentioned the condition for increasing and decreasing. A function y is equal to f of x is increasing value. A function y equal to f of x is increasing value. You have studied in PUC. If dy by dx is greater than 0, Derivative value greater than 0, then function is increasing. Increasing and climbing up. A function y is equal to f of x is decreasing. A downward arrow for decreasing, upward arrow for increasing. A function is decreasing if dy by dx value is negative. Derivative value positive for increasing, derivative value negative for decreasing. Fine? Okay. So derivative positive for increasing, derivative negative for decreasing. I'll be back to this increasing, decreasing later on, because I have already written the statement of Rolle's theorem. I would like to prove it. I have to explain the proof of the theorem, and I will come back to visit these topics again later, because it is required later on. We are going to discuss it later. Okay? Fine? So, Unit 1 only, the first main result we are going to prove is this Rolle's theorem. Exam only, pakka 6 mark question, guaranteed essay type question for you. We used to give the question as state and prove the book. State and prove Rolle's theorem. State and prove Rolle's theorem. Okay. Statement 1. If a function is such that it is continuous on the closed interval AB, closed ಅಂದರೆ ಬರೆಯಬಹುದು on the closed interval AB, closed interval AB, differentiable on the open interval AB, and values at the end points are equal. In fact, we have studied Rolle's theorem and mean value theorem in PUC. You prove ಮಾಡಿಲ್ಲ, but theorem statement ಕಲ್ತಿದ್ದೀರಾ. You answered question in the board exam. Find the values of C satisfying Rolle's theorem. Find the values of C satisfying mean value theorem. We have studied. So we are proving now. Functions should be continuous in the closed interval, differentiable in the open interval, right? Values at the end point are equal. F of A is equal to F of B. Values at the end point of the interval must be same. Then conclusion. There exists some number C in the open interval AB for which f dash C is equal to 0. F dash C is 0. Right? F dash C is 0 is a conclusion to the Rolle's theorem. There is a geometrical meaning of it. Right? The continuity is there in the closed interval AB, and in between A and B at each point is differentiable. Tangents exist. Tangent exists. Fine. Then values at the end point are equal. F of A equal to F of B. Here it is 0 because x-axis, the y-axis. On the x-axis, y value is 0. F of A 0, F of B 0. So they are equal. Values at the end points are equal. Fine. Okay. Now the question is, what do you mean by saying that f dash C is 0? What is the geometrical meaning of Rolle's theorem? Please look at the increasing and decreasing graph. A graph of a function is increasing. Graph of a function is increasing if dy by dx is positive. Graph of a function is decreasing if dy by dx is negative. Decreasing, derivative negative. Increasing, derivative positive. At a point C, where the derivative is 0, f dash C is 0. Right? That is the Rolle's theorem. We are talking about Rolle's theorem is that. You have a point C in the open interval AB, in between A and B. In between A and B, you are finding an interior point C at which derivative value is 0. You tell me now, geometrically what do you mean by dy by dx? Dy by dx stands for what? Dy by dx stands for what? Dy by dx stands for slope of tangent. M equal to tan theta. Slope of tangent. Dy by dx is slope of tangent. Slope of tangent 0. Please look at two cases here. Two cases. Slope of tangent. Currently, tangent to the slope dy by dx 0. The tangent is parallel to x-axis. Suppose it's like this. The tangent is perpendicular. This is vertical tangent. dy by dx is infinity. Theta 90. Theta 90 ಅಂದರೆ tan 90 infinity. dy by dx is infinity. Fine. Tan theta, theta 90 ಇರುವಾಗ infinity. Slope infinity. Slope infinity ಇದ್ರೆ tan it is vertical. Slope 0 ಇದ್ರೆ tan it is horizontal. Therefore, what does Rolle's theorem says? Rolle's theorem says that if a function is continuous in the closed interval and differentiable in the open interval AB and values of the function at the end points are equal, f of a equal to f of b, then there exists some number c in the open interval AB for which f dash c is 0. By saying that f dash c is 0, we mean that at some point c between a and b, there is a horizontal tangent. Horizontal tangent is tangent parallel to x-axis. Horizontal tangent. There exists horizontal tangent. Horizontal tangent at c. This is a conclusion of Rolle's theorem. Geometrically, Rolle's theorem means that there exists a horizontal tangent at some point c between a and b. Between a and b is at an interior point. Fine? Okay. Now look at the proof. So I'll quickly give the proof. Assume that function is continuous in the closed interval AB. If the function is continuous in the closed interval AB, we have written two theorems there. Starting ಅಲ್ಲಿ ಎರಡು theorem mention ಮಾಡಬೇಕು. ಒಂದು extreme value theorem. Extreme value theorem says that if a function is continuous in the closed interval AB, it has an absolute maximum or an absolute minimum value in the interval AB. Absolute maximum and absolute minimum in the interval AB. Right? My starting first line in the proof is this. Since the function is continuous in the closed interval AB, by extreme value theorem, right, function may have an absolute maximum value or absolute minimum value in the interval AB. Fine. The absolute maximum or the absolute minimum value, where these values can occur. Absolute maximum and absolute minimum values can occur where? Right? It may occur. First case, I have three possibilities before me. We have three possibilities before me. The first one, the value may occur at a point C. At some point C in the open interval AB, at which f dash c is 0. Right? At some point C between A and B for which derivative is 0. Derivative is 0 ಅಂದರೆ derivative C value is critical number value. Right? Absolute maximum and absolute minimum can occur where in the question. It may be at a critical point where f dash c is 0. It may be at a point C where f dash c does not exist. F dash c does not exist. Critical number ಗೆ ಇನ್ನೊಂದು possibility ಇದು. It does not exist. Okay. Either it is point at which derivative is 0 or point at which derivative does not exist, or the third possibility is at the end points of the closed interval AB. These are the three possibilities. Okay. Now ask a question to yourself, whether case 2 arises here, whether case 2 is going to work here. No, because in the hypothesis of the theorem, Rolle's theorem in the hypothesis ಅಲ್ಲಿ ಮೂರು ಸ್ಟೇಟ್ಮೆಂಟ್ ಉಂಟು. ಒಂದು continuity in the closed interval, functions differentiable in the open interval, values at end points are equal. There are three things in hypothesis. The second one says that function is differentiable at every point in the open interval AB. Since the function is differentiable, function is assured to be differentiable on the open interval AB, the case 2 doesn't arise. Derivative does not exist at an interior point C. Doesn't arise because it's guaranteed that the function is differentiable on the open interval AB. Is it clear? Function is given to be differentiable on the opening to AB. Therefore, the points at which derivative does not exist, this case doesn't arise. Okay, fine. First case the derivative where derivative exists, find the point at which derivative value is 0. Find the possibilities 1 and 3 you have to work it out. Possibilities 1 and 3 you have to study. Right? Possibilities 1 and 3 what you have? Right? Possibilities 1 and 3. I have just put it in the next video as already video is getting lengthier. Okay, I'm going to discuss this today itself, but I will put it in the next video.